Okay, well, thank you very much for the invitation. I'm sorry I could not make it to India for. I'm sorry I could not make it for the on live meeting, but it's a very busy time of the year here in America, North America. So I'd like to perhaps give a talk on something that is a bit on the fringes in relation to this meeting, and I want to talk about something that I started working a few years ago with mostly undergraduate students, which is the topic of collective ordering of dipoles in nanocavities, in particular in gemstones. And so what I want to do is to expose you to this topic. I'm not going to get into very technical details, and we'll see where we go with this. Okay, so let me tell you right away what I'm hoping you will take out of this talk. One point is that there's perhaps some interesting strongly correlated physics at play in nano-confined quantum electric dipole molecular systems, like quantum rotors, really, in carbon C60, fullerenes, and gemstones such as beryl, cordierite, and so on. And these systems are perhaps a fruitful platform for the study of frustrated or topics of frustrated of interest to the community of frustrated magnetism. For example, phenomena or properties such as quantum fluctuations, quantum disordered phases, quantum criticality, quantum and thermal order by disorder, spin translation coupling effect. And here we're talking about not spin, but the rotation, degrees of freedom, crystal field effect, and foremost, quantum random disorder. And so this talk will be rather simple and introductory, trying to bring these ideas to the fore for these systems. So this work has been mostly done over the last 3 years by undergraduate students in marked here: Beaulieu, William Hemphill, Addison Richards, Ying Liu, who now have moved to greater ventures, and Yulia Kelugina, who's a PDF in chemistry at Waterloo, and Jeff Rao, some of you might know him, who was a PDF with me, and now he's an assistant prof at the University of Windsor in Canada. Okay, so this is the outline of my talk. So I want to give you first a long preamble on the topic of frustrated dipolar magnetic systems that will set the stage about many of the features that will come up as I move along with the talk about confined quantum rotors, and talk about the models that we have considered and the method we've used, and then present some results on both C60 and beryl, and then conclude. Okay, so most of you will know about the topic of quantum phase transitions. And in Subir Sachdev's book, right in chapter 1, he discusses two central problems or models that display this kind of phenomenology, where you have a control parameter, G, that drives a transition at 0 temperature between what would be an ordered phase, let's say a long-range ferromagnetic phase, to a quantum disordered phase, a quantum paramagnetic phase. And then in sufficiently high dimension, or if frustration is not too high, then there would be a phase transition, a thermally driven phase transition between the trivial thermal paramagnet to the ordered phase as you lower the temperature for a tuning parameter G, which is less than the critical value GC. So there are two models that have attracted significant attention for in the context of insulating magnetic systems or insulating systems without free fermions. One of them is the transverse field Ising model, written here, where you have two terms that compete. You have an interaction term written here in terms of coupling between the Pauli matrices, the sigma Z Pauli matrices. This is a bilinear coupling term. And then you have a competing single spin term, which is what is referred to as the transverse field, which is proportional to 1 power of the sigma x, the Pauli matrix. And the main feature that drives the quantum phenomena in this model is the fact that sigma x and sigma z do not commute. And so depending on the limit of whether or not G is 0 or G is very large, then the system endeavors at 0 temperature to extremize the minimum energy state, which corresponds to either a long-range ordered phase, a direct product of sigma z, or a fully polarized state where the eigenstates are corresponds to spins or magnetic moments pointing along the x direction. Another model that has also been extensively studied is the quantum rotor model, where now we have an ON model, vectors of with n components, represented here by these unit vectors n hat at site I and j, nearest neighbor interaction. And then the term that competes with this interaction is also a single body term, but now it's an angular momentum signified here by the this rigid rotor term, sum over each site, L squared. So what I want to do in talking about these confined quantum rotors is essentially make use of this model here, or find rather a context where this quantum rotor model comes to life, but with a sophistication of both of these terms. Okay, so in terms of experimental settings, there's many realization of these two systems, the transverse field Ising model and the quantum rotor model. I've listed them here. They are briefly reviewed in Subhro's book in the first chapter. For time consideration, I'll jump over all of these and focus mostly on the lithium holmium fluoride, because it will set the stage for many of the topics coming up for the confined quantum rotors. So lithium holmium fluoride is an insulating magnetic material. It has 4 atoms per unit cell. It's a body-centered tetragonal primitive unit cell, and then the holmium ion here is the ion that carries the magnetic moment. And so the way that one arrives at the transverse field Ising model description for this material proceeds through a number of steps. First of all, there is a large crystal field acting on the holmium ion, which forces the holmium magnetic moment to be essentially described by an Ising pseudo spin, where the magnetic moments are at low temperature constrained to point along the crystallographic c-axis. And so the z direction here corresponds to the global c-axis of the crystal. This crystal field produces a crystal field doublet for the holmium ion, and it's that doublet that is represented by an Ising variable. The magnetic moment on the holmium is quite large. It's about 7 Bohr magneton, and the principal interaction between the magnetic moments in that system is actually originates from the long-range magnetostatic dipole-dipole interaction written here for the Hamiltonian in terms of the magnetic moment of the holmium ion. And in absence of other terms in the theory, which are like exchange and transverse field or magnetoelastic coupling, the magnetic moment here is again proportional to, can be shown to be proportional to the sigma z Pauli matrix, and with z pointing along the c-axis. What's interesting about this material is that it can be, the holmium ions can be diluted by a non-magnetic yttrium 3+, and the dilution of the holmium by the yttrium causes minimal local deformation. And so one can explore the physics of this material in finite transverse field or in zero transverse field, both for the pure case, lithium holmium fluoride, or in presence of non-magnetic dilution of the holmium ion. The physical magnetic field in that system that causes the fluctuations is a transverse field that is applied perpendicular to the c-axis. So for example, along the a-axis, represented here by this magenta arrow. And the transverse field gamma that appears in the transverse field Ising model arise in this material from that mixing, a field-induced and mixing between the ground doublet. So here's an energy diagram of the low energy crystal field of this material. At zero field, we have an Ising doublet, which is separated by an excited crystal field singlet at an energy of about 1 millielectron volt or 10 Kelvin. And it's the transverse field produces and then mixing between those crystal field doublet states here and the excited singlet, such that as the applied field B is increased, we get a doublet split or splitting of the ground doublet, which is proportional to the square of this applied field. And the excited singlet gets repelled by the ground doublet. And the transverse field term originates represents the splitting between the originally two degenerate crystal field states. And so so the phase diagram of this material is quite rich. In zero dilution, that is for lithium aluminum fluoride, there's a phase transition between at finite temperature of 1.5 Kelvin between a paramagnetic state and a ferromagnetic state, and the application of a transverse field causes a depression of the ferromagnetic phase, and the quantum critical point where the ferromagnetism disappears at the lowest temperature is of the order of 5 Tesla, so quite achievable in the in-house experiment. Now, this is the phase diagram which shows the three-dimensional phase diagram as a function of temperature and transverse magnetic field. So this phase diagram here in the middle panel corresponds to the plane here for x equals 1, where we see that as the magnetic field is increased, we depress the phase transition. But there is also physics driven by the dilution of the holmium as x decreases, and we replace the holmium side by yttrium ions. The phase transition in the Bx equals 0 plane decreases, the ferromagnetic phase Tc decreases, and eventually at about 25% of occupation of the holmium side by holmium ions, one gets into a dipolar spin glass phase. So one can also study the depression or the destruction of the spin glass phase when applying a transverse field to this Ising dipolar spin glass system. And there's been a lot of effort over the last 30 years trying to understand the details of that phase diagram and what's the physics operating in there. So, so let's carry on with this mindset about and discuss magnetic dipoles and highly frustrated magnets. In contrast with what Martin Muigal just mentioned, we're talking here about systems which are rare earths, for example, as in the lithium aluminum fluoride. Superexchange is small in these systems, and they often carry a large magnetic moment. So the dipolar interactions is often the leading interaction in such systems. It's pretty clear right now in the field of frustrated magnetism that the original or the older perspective that only SU2 or real spin 1/2 systems with isotropic Heisenberg antiferromagnetic exchange interaction are the only system interesting. This perspective is nowhere near as common as it was perhaps 10 years ago. And two reasons for that is that there's been ample work done on Kitaev materials and systems which have enormous strong spin orbit interactions, where the Hamiltonian describing the systems is strongly anisotropic. And there's enormously rich physics occurring in the Kitaev materials. Similarly, in the rare earth part or materials, which have a chemical formula written here, where the rare earth ion, praseodymium, neodymium, and so on, reside on the lattice of corner share tetrahedra. Experiments have shown over the years that there's many interesting phenomena occurring in these materials. So the question is are there other types of materials where the long-range magnetic dipole-dipole interactions are interesting, in addition to those displayed by the rare earth particle materials here? And what would those be? Well, I've already mentioned the physics of the lithium aluminum fluoride in the transverse field, but it turns out that when you dilute this material, the action of a transverse magnetic field generates other terms in the effective low energy Hamiltonian, which are random field terms. So in fact, lithium holmium fluoride in a transverse field, when holmium is diluted by yttrium, becomes a textbook realization of the famous random field Ising model, albeit that the random fields in that case are correlated random fields. In the case of the Parker systems, there is the phenomena of dipolar spin ice physics, where the dipolar interactions are themselves responsible for the spin ice phenomena in these materials, but also the excitations, the spin flips, otherwise referred to as monopoles in these systems, display effective Coulomb-like 1/r interactions, and that these interactions between the monopoles originate from the microscopic dipole-dipole interactions. In gallium titanate, we have interesting partially ordered multiple case structures, and as a last example, gadolinium gallium garnet, or otherwise known as GGG, has a very rich and poorly understood phase diagrams, and even possibly a low temperature or an intermediate field quantum disordered phase that is not really well understood. So what are the possible other avenues for dipolar systems? Well, while they are interesting, rare earth 4F dipolar magnets have some issues with them, some problems. First of all, foremost is that the energy in the temperature scale is low, 1 Kelvin. And this is good on one hand because it allows to reach a very rich field-driven physics in house labs. But the problem is that if you would want to identify a situation where your dipole are freely rotating, like the equivalent of a 3-component Heisenberg model or 3-component dipoles, this is very difficult to achieve for rare earths because the crystal field effects will typically be huge, and that will cause the systems to be either Ising-like or XY effective pseudo spins. This may be less the case for gadolinium, but the details of where and when this may occur for gadolinium is not settled. So, so the idea is to look at completely different systems, and the one that I want to talk about are molecular electric dipoles confined in nanocavities. And so this is interesting from the point of view of new phenomena, materials, but in energy scale, but also that it becomes a realization of an anisotropic quantum rotor model. And so what we have is an upgrade, if you wish, of the quantum ON rotor model that I mentioned in the second slide of the talk, where we again have angular momenta here as the single particle term in the Hamiltonian, the kinetic rotational energy, but now our rotors are not coupled by an isotropic ON type interaction, but by a long-range dipole-dipole interaction. And the physics, the physics operating here, the quantum mechanics, originates from the fact that the dipole operators do not commute with the angular momentum operator. So, so let's switch gear a bit and talk about what kind of nanocavities we're talking about. Well, one context which has been extensively studied by physical chemists over the last 20 years is the topic of molecular surgery. So in these systems, through a very complicated sequence of chemical reactions, what has been found and demonstrated to be possible is to take C60 fullerenes samples, microscopic samples, and subject them to a chain of chemical reactions that causes the buckyballs, the C60 molecules, to open up and intake small molecules. And so small molecules that have been inserted in the C60 molecules are molecular hydrogen, deuterium, hydrogen fluoride a few years ago, water, and also heavy water. And so what is phenomenal about this procedure that is now actually as crossover to physicists who are making use of these techniques is that the attack of the C16 molecule not only opens the molecules or the cages and allowing the small molecules to enter it, but at the end of the chain of reactions, those C16 molecules, those cages can be actually restored to their original structure, and the cages close, encapsulating the host, the water molecules, for example. And so, so the water molecules in the gas phase has an electric dipole moment of about 1.8 dBi. This is an energy scale in the hundreds of Kelvin for water molecules separated by a few angstrom. So you immediately see the idea here is that one gets energy scales, dipole energy scales, which are boosted by 2 orders of magnitude compared to magnetic dipole interactions in the context of magnetism. So there's been a huge amount of experimental and theoretical interest devoted to understanding the effects of the carbon atoms in the C16 molecules on the rotational and translational degrees of freedom of encapsulated molecules. And in the case of hydrogen and deuterium, the interactions between the molecules and those in the vicinity, the other encapsulated molecules, is very weak because these interactions would be electric quadrupolar and so extremely small. But the ability to encapsulate dipoles such as hydrogen fluoride and water opens the route to explore the physics of the collective physics of dipole interactions for these systems. Okay, so so this is interesting because if you omit the details that C60 has a structural phase transition at about 300 Kelvin from a crystallographic FCC to a simple cubic lattice, if you just consider the center of mass and neglect the relative orientation of the cages, the center of the C60 continued to define a face-centered cubic lattice below this structural transition. So in a sense, as a first approximation, the encapsulation of dipoles in C60 realizes a face-centered cubic system of rotating 3-component dipoles. And this is interesting because it's been, in part because it's been known for 60 years that on the face-centered cubic lattice and on the body-centered cubic lattice, classical dipoles should exhibit a ferroelectric or ferromagnetic phase if they are freely rotating. And so this was already anticipated by the work of Swarovski and Nana Yakara in 1992, where they argued that if one were able to encapsulate electric dipoles in fullerenes, one would be able to generate this kind of phenomena, have dipoles in an FCC lattice. Of course, this is in a context where one is ignoring the cage deformation and the coupling between rotation and translation of the water molecules within the cage. But let's carry on with this minimal description and ask what's possible in terms of the competition between the dipolar interaction and the kinetic rotational energy of such rotors on a face-centered cubic lattice. Okay, so these experiments have been done. Some results were already reported for the case of water in C60. So what was measured was the real and imagined part of the dielectric permittivity. And what one expects is that if there was a ferroelectric phase transition in such a system, the real part of the dielectric constant would have a singularity at the phase transition. And so these experiments found no evidence for a phase transition for water in C60 down to 8 Kelvin or so. And this is really the first work that launched the interest in exploring the collective behavior of dipoles in the C60. So this lack of a long-range order down to such a low temperature, much smaller than the energy scale of the nearest neighbor electric dipole interaction for water on the crystal of C60, already raises the question of what's the physics going on that prevents the spontaneous ordering of the dipole interaction. And so this is kind of the story that sets the stage for this problem. Okay, so how do we understand the physics very simply of what's going on in the system? Well, in the limit where there's no interactions between the, let's say, linear rotors, we know what is the energy spectrum of a linear rotor. It's an undergraduate quantum mechanics textbook. We have a ladder of energy levels where the energy of these levels goes like L times L plus 1. And so the ground state is a fully symmetric S waves type order, is a singlet. Then the first excited state at an energy of 2 times what's called the rotational constant, which is h bar square over 2I, where I is the moment of inertia of the molecule or the rotor. And then as one increases with the quantum number L, the energy spacing between successive energy level increases. And so the ground state is a symmetric state. It carries no expectation value of the dipole moment. So that's the limit of the very large quantum limit. So the control parameter G that drives the quantum phase transition that I mentioned in the earlier slide is essentially controlled here by 1 over I. The smaller, the lighter is the molecule, the smaller its size, the more quantum it is. Conversely, in the limit where we have very large or very massive particles, classical-like or very strong dipole interaction, then the minimum energy would be reached at low temperature by extremizing the dipole-dipole interaction. And one would expect to have some kind of phase diagram where we have a regime of dipolar ordered rotors to a regime at small moment of inertia where we have a quantum disordered phase. And so as a cartoon, this is what we expect for the phase diagram. That has not been actually reported as far as I know for this kind of systems. And so what I will present to you today is, I believe, the first survey of that kind of phenomenology within a very limited theoretical perspective. And so this is the phase diagram as a cartoon. KB, T here is the thermal energy, T is the temperature, B is the rotational constant for the linear rotor, h bar square over 2I. And the horizontal axis is the ratio of the dipole-dipole interaction energy scale divided again by the rotational constant. So the two axes here are dimensionless, and sigma here is a placeholder for the dipolar lattice sum for the system. The long-range dipole-dipole interaction here has to be handled with without truncating this dipole interaction, and so it has to be computed using Ewald summation method, for example. And so in the limit, in the classical regime, where the moment of inertia is very large, one finds that the critical temperature between the pielectric phase and the ferroelectric phase is proportional to the dipolar energy scale. And this regime here, this classical regime, the phase diagram, the phase boundary lives on a straight line extending to infinity for infinite dipole interaction. As one decreases the rotational, the moment of inertia, or increase the rotational constant, the phase transition temperature, the critical temperature decreases up to a point where one reaches a quantum critical point, and beyond which there is a quantum disordered phase. So the first question that one wants to ask is, for the context of, for example, C60 or C70 or other fullerenes, which are also amenable to this molecular surgery method, where are we for a given host molecule in this type of phase diagram? So this is the first question that we ask in this type of project, and that my students pursued. Okay, so so what's the physics? What's going on? Well, the free rotors at low temperature, when the temperature is lesser than the rotational constant, they are essentially in a symmetric zero dipole average singlet state. This is similar to a number of magnetic systems where the singlet single ion ground state is separated by a finite energy to finite crystal field levels. So this kind of physics, for example, occurs in lithium thulium. That should be a O4 here, F4. Sorry, I apologize for that. And as well as metallic praseodymium. Praseodymium as a metal would have a singlet ground state. It shouldn't be magnetic, but because of the low-lying crystal field level of praseodymium, praseodymium as a metal is actually ordered, magnetically ordered at low temperature. So the interaction here, the dipole-dipole interaction, admits the excited rotational states in the ground state, entangling them into that state. And ultimately, this bootstrapping leads to the development of an internal dipolar field, which gives rise to collective long-range order if the dipolar interactions are large enough. So in a sense, it's the problem here is a self-consistent Stark shifting or Stark effect. And then once this internal electric field is large enough, then there's a phase transition at finite temperature that can occur. Okay, so there's many things one can consider. We consider linear rotors, symmetric rotor like ammonia, asymmetric rotor like water. One can consider nuclear spin statistics. So, for example, if you think about H2O, the two protons that are fermions, and so a rotation by pi about the rigid body of the water molecule exchange the two fermions. So that means that there is a constraint on what angular momenta the water molecule can have in relationship to the nuclear spins of the two protons. This is very similar to the topic of auto and para symmetry in molecular hydrogen. From a point of view of experiment, one may be concerned about the finite concentration of dipoles that occupy the encapsulating cages. And as I mentioned before, there is also some phenomena akin to Yan-Taylor distortion, which would correspond to a spontaneous distortion of the cage in response to the presence of a host, the rotational translational coupling of the molecules, and so on. We are really at the beginning of this field in terms of looking at collective behavior. I want to make a point here that in the case of C60, depending of the commitment or the effort devoted to the synthesis or the details of the methodology, the cage occupation in the case of water in C60 in the initial works was at the order of 30%, but now experimentalists are able to reach cage occupation, which is close to 100%. This will be different when I discuss the topic of encapsulation of water in the gemstones. Okay, so what's the model? Well, I won't get into the mathematical details. I don't want to spend much time talking about Clebsch-Gordon's and all the mathematics we had to deal with to solve this problem. Let me just give you a kind of picture of what's the idea. So we have two terms in our Hamiltonian. We have rotational kinetic energy. We have long-range dipolar interaction. These dipolar interactions are written here. We have simplified the problem. We consider that there's only one axis of the molecule that carries the predominant dipole moment. We can rewrite this dipolar interaction in terms of bilinear couplings, in terms of unit vectors here. And in the most general case of an asymmetric rotor, one would have three rotational constants associated to three principal axes of rotation, and these rotational constants take the name capital A, capital B, and capital C. For a linear rotor, there's only one rotational constant, and I will mostly focus on this case for illustration purposes. So the method we took to survey what's possible in terms of phase diagram for these systems is a simple mean field or artery decoupling of the dipolar term and mapping this problem on a self-consistent Stark effect and solving for the critical temperature and the internal polarization of that system and constructing phase diagrams. Okay, so this is to illustrate as a cartoon what we find. For linear rotor, we find that the phase diagram is quite simple. It corresponds to what I illustrated earlier. There is for lambda here is a trax is a scale parameter that is proportional to the square of the dipole moment and the lattice sum, the FCC dipolar lattice sum. B is again the rotational constant, and tau here is a reduced temperature, which is the physical temperature divided by the rotational constant. So same phase diagram as I illustrated earlier, a paraelectric phase, a ferroelectric phase at low temperature if the moment of inertia is sufficiently large in the semi-classical regime, and a quantum disordered phase where there is no longer ferroelectric phase. The symmetric rotor, which corresponds to a molecule that would be akin to a prolate or a noblate, a pancake type molecule. So for example, ammonia would be a realization of a symmetric rotor. Ammonia can be inserted in C60. There is again a ferroelectric phase and a paraelectric phase, but what's interesting in this case is depending on the aspect ratio, the ratio of 2 of the rotational constant, one can have an interesting reentrance phenomena here. For example, if the molecules tend to be oblate-like, that is pancake-like, there is an insertion of the ferroelectric phase above the quantum disordered phase. And that is to do with the fact that the excited rotational energy levels carry more dipolar character than the lowest one. And so as those states become thermally populated, as one increases the temperature from the quantum disordered phase, one would actually enter into a ferroelectric phase and eventually, upon further increasing the temperature, return to the paraelectric phase. That has this kind of phenomena has nowhere near been explored in encapsulated dipole molecules thus far. For water, the phase diagram is similar to the linear rotor. And this is a phase diagram for where we have made use of explicitly of the rotational constant of water, but depending whether or not we have auto or para water, meaning what are the nuclear spins of the protons for water, the phase diagram is slightly different. So what's the outcome of this work in the case of encapsulated water molecules in C60? For those molecules that have been thus far synthesized, which is hydrogen fluoride, HF, which is a linear rotor, ammonia, NH3, and the asymmetric rotor, such as water, H2O, and heavy water, D2O, what we find is that those molecules should be very deep in the quantum disordered phase. That is, they are so quantum that the energy spacing between the ground state and the first rotational state is very large compared to the dipolar interactions that would describe them. Furthermore, the dipole moment is screen here is reduced by about a factor 3 compared to the gas phase dipole moment. And so these molecules should not exhibit spontaneous ferroelectric order according to our calculations. Tentatively, this is consistent with what has been seen experimentally for HF and H2O, where no spontaneous formation of a ferroelectric has been found. The density function theory calculations suggest that it should be possible to insert lithium chloride, sodium fluoride, and sodium chloride in C60 molecules, but that has not been done thus far. And one will have to see whether or not those molecules are actually sufficiently small that they can be inserted into C60 cages without destroying the cage or distorting it too much. But if this was possible, our calculations predict that there should be ferroelectric phase in these systems, but we'll have to wait and see what experiments reveal and what proves to be possible for these more classical molecules, and whether or not they are perhaps at the verge of a quantum disordered phase. Let me shift gear gears and talk about burial. This is a more recent development.
Michel, if you can wrap up in like a couple of minutes or so.
Sure. Thank you. So, so burial is interesting. These are gemstones like emerald and so on. And so, so what one finds in these systems is that they don't form a face-centered cubic lattice, but in fact they are hexagonal structures where there are cages that can host the water molecules, which form an hexagonal lattice. So when one has an AAA type stacking of the dipoles, which is illustrated here, and the occupation of those cages is of the order of 30 to 50%. And so, so the question is, what happens in that system? There is evidence that there is a saturation of the dielectric permittivity in the systems below 10 Kelvin. But again, we ask, where are we in terms of phase diagram, possible phases for encapsulated water in such a systems? So let me immediately jump to the results. And so what we find is that the semi-classical ground state in these systems is interesting. Each hexagonal layer consists of dipoles which are polarized in a common direction, but from one hexagonal layer to the other, the relative orientation of the dipole flips by pi. But within a given plane, those dipoles are free to rotate. So there is there's a degeneracy that exists in the system where the dipoles essentially behave like XY rotors. So according to our calculations, given the uncertainty on the dipole moment, if all the cages were occupied, we would expect that there would be a phase transition between a pielectric phase and a coplanar anti-ferroelectric phase in a range of temperature between 35 and 20 Kelvin for these systems. This is not seen. There is, as I mentioned, a saturation of the dielectric permittivity. And one of the questions that we ask is what's the role of finite concentration of the cages by water molecules? So we've explored how the ordered states evolve. This anti-ferroelectric phase evolves as a function of concentration of the cage. And what we are discovering, this is work in progress, is that irrespective of the concentration of the cages, that is, irrespective of the what fraction of the cages are occupied by electric dipole moment, we seem to be progressively always losing long-range order as the system size increases. And so this is interesting because it reminds us of a well-known result by Amnon Harani in the 70s, where he argued that when you have systems where you have off-diagonal anisotropic interaction, that the fluctuations of the low energy fluctuations away from the long-range ordered phase in such systems are infrared divergent below 4 dimensions. And so this is these interactions would then destroy any possible spontaneously ordered continuous symmetry phases and give rise to a glass phase. This is reminds us of the topic of the Bragg glass for the random field XY model, for example, where in less than in 3 dimensions there is a speculation that the system would have algebraic order. So when we ask what happens here in the presence of the dipole interactions for these planar routers, whether or not one has an exotic phase if the fraction of the cages occupied is sufficiently large, but the answer to that question is not known. In fact, there's still some debate what is the nature of the ground state for the random field XY model, and clearly more experiments are needed to try to tie together these theoretical ideas that I mentioned in my talk and what's going on the experimental front. So let me put my conclusion, show my conclusion, and just to recap, tell you, I hope I conveyed the message that there's some fledgling interesting physics available when considering quantum rotor systems in nanocavities. There's two avenues to explore that: C60 through molecular surgery, and water that is present in gemstones such as beryl, for example, and emerald, and that there's many interesting effects of interest to the statistical mechanics community and the frustrated magnetism community, such as thermal fluctuations, quantum fluctuations, random disorder, even the possibility of quantum and thermal ordered by disorder for the case of dipoles in the beryl cases, to lift the degeneracy, this accidental degeneracy that I mentioned for the dipoles in plane of each hexagonal layers. Thank you very much for your attention.
Thank you, Michel.
Thank you.
Do we have any questions?
Michel, it's a fantastic talk, and
thank you.
I have one question about this. I mean, to me, it looks like a quantum liquid, because if the first few levels of the rotational levels are important, like the ground state and the first excited state, it's close to spin 1 or spin half system. So it could be thought of as a quantum spin liquid. Then in which case, the question arises, what are the nature of excitations? Because such questions have been asked in the context of quantum paraelectric, namely strontium titanate.
Right, thank you. Yes, so right, so the so in this system bears many this kind of system bears many similarities to dominant wall, for example, in the transverse Fehlheising model, in the 1D transverse Fehlheising model, but also rotons, right? So one can imagine doing rotational wave expansion or flavor wave expansion in a quantum disordered phase. I have not thought or explored this topic yet. I really don't know what the nature of those excitations would be. One doesn't have the symmetry that we have for the quantum rotor model that I mentioned earlier. One doesn't have an ON symmetry because of the dipolar interactions. So it would be interesting to explore what is the nature of those excitations. On the experimental front, I think it appears likely that one is really very deep in the quantum disordered phase for the case of water in C60. I guess that's all I can say about this for now. But it's true that it also, in the case of strontium titanate, where, for example, there's something, strontium titanate is, I guess, closer to a spontaneous ferroelectric phase, because I believe that if you replace oxygen by its heavy isotopes, then there is evidence that it's ferroelectric. Is that right?
Barium titanate is ferroelectric.
Right.
Strontium titanate is quantum paraelectric.
Yeah, but I think that if you replace the oxygen O16 by O18, I believe that perhaps then it goes ferroelectric, right?
That's right. Yeah.
Yeah. So strontium titanate is very close to, in a sense,
to,
the quantum critical point. I think the most promising directions are these gemstones, but then there's many peripheral issues that has to be debunked to figure out what's going on.
So sitting in Bangalore, sitting in Bangalore, I cannot resist making a remark about gemstone. Please show the last picture. You had the picture of the gemstone. Where, yeah. See, C.V. Raman was fond of collecting gemstones. So there is a museum in Raman Research Institute at Bangalore, which is about 10 miles away from here, where there are gemstones where you can see water trapped inside, not nano cavities, but water droplets. So it's a transparent gemstone. So you can see water. I was fascinated. This is created by geological processes.
That's right.
So there are gemstones which water, spots like millimeter size.
I see. So, interesting.
It will be, I think I encourage people to visit the lab in Raman Research Institute and enjoy gemstones. You are also most welcome to visit India.
Thank you. Thank you. Thank you for the questions and the comment.
Yes. Hi, Michel. Just a simple question. I mean, if you have the water molecules rotating fast, they will also produce a magnetic moment. So don't you expect that? I mean, you have like, I mean, in one regime, you have all the dipoles, electric dipoles. In the para-electric regime, you may have some ordered magnetic moments.
Okay, well, that would be, okay, so yeah, well, I guess one can already ask the questions of a single rotor, right, in quantum mechanics. And if you have an electric operator there, and then you have these dipoles, electric dipoles rotating, they produce magnetic field. That's I guess that's certainly possible physically, but I think you know, it's a relativist. It's going to be a relativistic effect, right? So I don't think in the context of what I'm talking about, I don't think I'm ready to worry about that yet. But I'm not even aware that I've seen this being discussed in the case of, you know, an undergraduate problem, if you wish, of two charges, positive and negative, sitting on a rigid rotor and treating the relativistic problem of what's the feedback effect, for example, of the radiation, like the QED problem of the charged linear rotor. I guess that should be a well-posed problem, but I'm not aware of having seen that in any textbooks. Are you?
Isn't it just a loop of wire where the electrons are running around? I mean, I'm confused a little bit.
Yeah, it is. Yes, it is.
Maybe not.
Yeah, but it would be a relativistic effect, right?
Okay. Good. Yeah, maybe.
Any more questions?
Hi, Michel. Yasir here.
Yes, yes.
Just on a lighter note, I think if Bhattacharjee had spoken to you about gemstones before, maybe that would have pulled you to Bangalore. He did a better job of advertising.
Well, maybe I should have told you earlier what I was
Title
hoping
is
to.
good to see you in.
Thank you. Thank you.
If I may, this is Martin here. Michel, you definitely
Martin.
need the updated picture with the Bangalore crystals with the water in it. So your talk will not be complete until you have that picture that Bhaskar suggested. But I just want to make a comment about you know, I was surprised not to see diffuse scattering calculations for the systems, structural diffuse scattering. I just want to point out that, you know, in neutron scattering, we have this great tool, which is hydrogen as a huge cross-section and deuterium as a small cross-section. So we can highlight water in crystals and things like that. The biologists do this all the time. So, you know, that could be a very interesting program to get neutron scatterers to get interested in. Some of them do. There already is some work on beryl and stuff like that. But just keep in mind that we can play with water, we can highlight it, and perhaps there's things we can do that reveal the physics more prominently.
Right.
And I don't know if you thought about it though.
I mean, there is neutron. There's work that has been done at Oak Ridge where they have looked. I mean, physical chemists are fascinated, as far as I can tell, from this problem of encapsulated molecules in C60, because it's kind of it's an exquisite platform for them to do spectroscopy and test their various calculation methods to look at infrared and Raman absorption cross-section, and what's the effect of an environment like the confining C60 cage on the energy levels of individual trap H2, HF, and H2O. And they certainly have done inelastic neutron scattering to probe those energy levels. But in terms of looking at correlation effects, I'm not sure that this has been done. So thank you for the comment. But I think in the case of beryl, I mean, this could be more interesting. But then As Baskin mentioned, the work that was done by Martin Dressel and co-workers were done on natural gemstones, where over geological times water got trapped in them, and so one would have to consider a synthesis of those crystals where maybe heavy water is encapsulated, but I don't think this has been done.
One can let it soak in heavy water for a couple of years, and maybe it will exchange.
Yeah, I don't know what kind of time scales. I mean, I don't know if you notice. I went really fast. The crystals that these people in Goshenov and co-workers consider, this is the size of the single crystal that they studied. It's a few cubic centimeters in size. So I don't know what's the time scale, and perhaps for one doesn't need to have such big crystals for some of the experiments, but I don't know what's the time scale for water to permeate through the most of this crystal. So I don't know if 2 years would do it.
I'm afraid that now we have to stop. It's almost 7 here in the evening. And let's thank Michel again.
Thank you very much. Have a good evening and a good dinner. I'm going to go have
Michel,
breakfast.
and thank you everyone in the session.
Thank you.
Hope to see you soon sometime. Yeah.
Thank you.
Thanks. Bye-bye.
Thank you. Bye-bye.